Welcome to the first webinar of the INAE Bangalore chapter. We've called it the Frontiers of Engineering webinar. And it's my pleasure to introduce the first speaker, Mr. Narender. He is a scientist D at DRDO in Hyderabad. Just a quick background, he did his master's from Aerospace Engineering in IISc, and his areas of interest are wave propagation in nanostructures, non-local continuum mechanics, aerodynamic heating, and thermostructural testing. He's also co-author of a book with the title Wave Propagation in Nanostructures. And I'm very happy to note that he received the INAE Young Engineer Award last year in 2019. So with this, I will let the speaker take over. Narender, can you please take over, and I'll share your video feed in a minute.
Yes. Thank you, sir. Yeah. Good evening, all. So today, now I will talk about slight information. I will give you about the thermostructural testing of full-scale airframe structures. So which we do at our lab using infrared heating. So now my outline is like I will give just very basic introduction about aerodynamic heating, what it is, then how that aerodynamic heating generates, like that some basic information. After that I will go to thermostructural testing, how we do at our lab, how do we create that aerodynamic heating at ground level, then what are the methods of testing are used to simulate the aerodynamic heating. Then I will give you slight some 4 case studies what we have done recently. Now, aerodynamic heating, actually aerodynamic heating occurs for all the high-speed flying vehicles, like whenever the aero object like missile, rocket, or any spacecraft which goes beyond the speed of sound will experience the aerodynamic heating. Aerodynamic heating mainly because of the it occurs mainly within the atmosphere due to the air properties. Like major property of the air which involves this aerodynamic heating is its viscosity. Because of this viscous nature of the air, it will stick to the surface very near to the skin of the airframe structure. So beyond that, it will go to beyond the surface, it will reach its free stream velocity. So apart from this, the aerodynamic heating also affects many properties of the like our thermophysical properties of the airframe section. Now how it generates. Now you see here I am showing you one missile. When this missile is flying at high speed, now you can see it will split the free stream air and moves forward. So as it moves forward, whatever the air very close to the surface of the structure will get stick onto the air. Initially this will have a total energy which composes of like a kinetic energy and thermal energy. Whenever this kinetic energy comes to 0 at the surface due to the no slip condition and friction of the air, so then this total energy, the kinetic energy will completely convert into thermal energy, because this has to convert to maintain the energy conservation, right? So due to this, the skin get heated up, and as it get heated up, it will pass on that heat into the airframe section through conduction mode. Then inside the airframe section, it may be conduction, convection, radiation, or multi-mode phenomena will be there. Now, our main aim is to protect the internal components from the external heating. So that how we do mainly by designing the by selecting the high temperature materials, or maybe using external thermal protection layer or internal thermal protection layer. So different schemes are available. So based on our requirement, we can choose. Now once this is designed, how to qualify it? So that is our main aim of the presentation. Now see why this thermostructural testing is needed. Now you see, as the temperature increases, all the metals will show a reduction in its strength. You can see here for a structural steel, from room temperature to 1000 degrees, the reduction in strength is almost 10% at higher temperatures. So obviously the strength reduces means the total properties will come down and its effectiveness also will come down. Now we have to by testing we can validate the design and also evaluate the performance of the airframe section. Then if it is a composite section, then we can also qualify its manufacturing process by conducting thermostructural testing. Now these are the various heating methods are explored over the timeline. Now you can see it started with electrical heating in 1850s. Then induction heating, electric arc heating, oscillatory heating, radio frequency heating, infrared heating in after 1950s. Then plasma arc heating. Then afterward graphite heating was also there. Now out of these various industrial heating methods, infrared heating is only used for simulating the aerodynamic heating at ground level because of its major properties like very good electrical controllability, and we can achieve any heating rate, right, with very fast, and also cooling also at very fast rate. Then we can also achieve uniform heating over the larger area, even a large area, not in small scale area, in very large area, like almost like we are in our lab, we are testing almost like 1.5 meter diameter section also we have tested in our lab. So 1.5 meter in diameter, almost 2.5 meters in length, like cylindrical sections we have tested using infrared heaters. And now actually main problem with infrared heating is surface emissivity. So we have to make surface very close to black body to simulate the perfect infrared heating and absorption also. So apart from this, it has some cons also, like all these infrared lamps which are assembled on the heater are fragile in nature because these are podge lamps. And one more problem is with short continuous operation. When we are heated up to its peak rating, then its life will come down. So life of the lamp may be at rated voltage, it will be around 10 minutes maximum. Now coming to infrared radiation. Now if you see total electromagnetic spectrum, this infrared radiation will fall between 0.5 microns to 1000 microns. So over this range, we can see only invisible part from 0.5 to almost like 100 micrometers. So this is further subdivided into three regions like short wave infrared, medium wave infrared, and far infrared. So out of these three, this short wave infrared is used for simulating the aerodynamic heating, like for heating any object. This short infrared heating ranges from 0.5 microns to 2 microns. From 2 to 100 microns, it is medium wave. So this medium wave infrared heating is used for all this car paint drying and paper drying industry and all that. Why the short wave infrared is used is because of its energy. We can have very high amount of energy and temperatures in the lower wavelengths. Now if you see Planck's energy distribution over the wavelength range within the infrared region, now you can see this formula E equal to C1 by lambda to the power of 5. This expression shows the Planck's energy distribution, infrared energy distribution over the wavelength. Now if you integrate this equation, this energy distribution over the wavelength range, you will get Stefan-Boltzmann equation, which will tell you about the total energy content within the wavelength band, that is directly proportional to fourth order of temperature. Now if you see the locus of the maximum power, that will give you a relation called Wien's displacement law, which will tell you about relation between temperature and wavelength. Now you can see here maximum temperature is inversely proportional to wavelength. As this wavelength becomes small, then we can achieve maximum temperatures at source level. This is I'm talking about source level. It means in our case source is filament, infrared lamp filament. Okay, that's why we are talking about short wave infrared lamps. So in medium and far wavelengths, we may not achieve that higher temperatures as compared to short wave. So this is one of the infrared lamp I'm showing here. It is a C-bent lamp. It is like bent like a C shape. So this is made up of quartz filament, clear quartz. Then inside it has a tungsten filament. You can see here the filament also. So it is coil type. So this filament mainly dictates the power of the lamp. I can say based on the diameter, then coil length, then number, its pitch, all the parameters will define the rating of the lamp, and along with the length. We have different various ratings we use, starting from 80 watt per centimeter to 360 watt per centimeter. This is called linear power density. Now, whenever this lamp, both ends are connected to a voltage difference, then current passes from negative end to positive end. As it passes, so the leads will be made up of copper, but this filament is directly connected to the copper leads via molybdenum foil. But this tungsten filament is a resistance. It acts as a resistance. So whenever this current passes through the filament over this entire length from the coils, so it will start heating. So that heating, it will start dissipating at high rate. Now you can see here, rate of change of the energy of the filament is direct equals to input V² by R, which is the electrical input, and losses like radiation. If you see in terms of electrical engineering point of view, it is called loss to the electrical machine. So that is radiation loss that we are using. That loss of the radiation we are using for heating our object. Now this is a cylindrical element. It will radiate from all over the 360 degrees. It will radiate. Now this side I can place our object, so which will see this part. But how to take this part also? So for that we use a reflector here. So based on our requirement, we can go to stainless steel reflector or gold coated reflector. That will, whatever the radiation falls on the reflector, it will again reflected back to the surface of the object. So this is the just overview about the IR lamp. So now there are various types of IR lamps available. So this you can see here, one planar heater assembled with all IR lamps. This is like conical heater. Then we have cylindrical, different shapes. Now here one more IR lamp. This is mainly used for heating the leading edge, very thin line type, leading edges of wings like that. So this lamp has inbuilt reflector, gold reflector. There are like two tubes will be there. One tube will contain the filament, other tube is coated with gold. So this tube will be cooled with water also. Okay, otherwise it will get heated up and it may melt also. So for that we have to pump with water. So this can, now we are having almost like 10 kilowatt lamp of this twin tube heaters. Now these are the various linear power densities we are using. So over this short wavelength range, our lamps can emit maximum peak power at 1.2 micrometers. Now this is one gold coated reflector assembled with IR lamps. Now you can see here, as you go away from the heater, our flux will come down drastically. Now you can see with respect to distance, at 50 mm distance from the heater, at rated power of 95 watt per 95% or 100%, I can get maximum 95 watt per centimeter square flux. Then if I move 50 mm away from the heater, my flux will come down to 70. So that much, almost like 25 watt per centimeter flux reduction will be there. So if you want more flux requirement, we have to keep our object very near to the heater. Then there will be a participating media between the heater and object also matters while receiving the radiation from the heater. Now this graph shows the characteristics of IR lamps when I give a full rated voltage. Now you can see I have given a voltage of 415 volts to a 4 kilowatt heater, 4 kilowatt lamp only. This is for lamp. Okay, so you can see here current is initially it is surged to almost like 17-18 amps, and it is settled at 10 amps. Now this initial part is due to surging mainly because of the cold resistance of the filament, initial resistance of the tungsten filament. Then we can calculate dynamic resistance. Now you can see within fraction of seconds it can reach to its rated power 4 kilowatt for a 415 volts rated voltage at very fast rate. That is the advantage of the IR heater. So here I am showing you one more heater which is in cylindrical segment of a cylindrical part. So this is having this is made up of SS316 low carbon steel material. Then it has a highly mirror finished reflector. So this is a backside of this heater is having all electrical connections isolated from the surface, metallic surface, through isolators. So we are having a three-phase delta connection for every 3 lamps. So all heaters will have multiples of 3 lamps. Now this you can see here, these are straight lamps. As you can see closely how it looks like. This heater also has water cooling for this, because this side it will undergo very high heating. So backside of this reflector will be cooled continuously using high pressurized water pumps. We almost pump like 50 liters per minute rate. Okay, this is another heater which is assembled with C-bent lamps. C-bent lamps look like this and straight bends look like this. What types of tests we do at our facility? Mainly initially we do with the sample level. For any development phase we may not go for direct complete full scale level test. If any insulating material is in development stage, then we will do a sample level for evaluating the effectiveness, like thermal barrier coatings or thermal protection systems will be initially tested at sample level. Once sample level tests are finished, then we will go for a full scale testing with coating. Then apart from this, we do qualification tests on all missile systems, which involves structural loading and heating, then differential pressurization and heating, then thermostructural testing of wings, fin, control surfaces with actuation, and also with functional tests on various electronic packages, antenna performance, everything online. With heating we can do here. Along with, now recently we are conducting thermostructural tests on ceramic radomes also. Since these ceramic radomes are highly brittle in nature, so with proper care and all, we are nowadays developed a separate facility for testing of thermostructural testing of ceramic radomes. Now the basic requirements for the tests. Now for any thermostructural test, our initial inputs are time temperature profiler or time heat flux profile based on the designer requirement. Now if you see time temperature profile is given to us, then what we will do, we will see whether it can be taken up, whether we can achieve that time temperature profile, what are the power needed, whether that heater is available, all that will work out based on the inputs. Then based on, we will also take the inputs of the article, what to be heated. So what are the thermophysical properties of the article, so how much energy is needed to raise the temperature of the article. Everything will be calculated, and based on that we will give feedback to the designer whether we can do this test or not. If it is, can we take it up, what type of fixtures needed, what type of heaters to be designed and realized, whether it can be done with available heaters. So all the things will be given in a standard format. Then apart from the temperature, we can do structural loads in 2 ways. Either we can do a differential pressure application, or we can go for a concentrated loads. So these concentrated loads are applied mainly to simulate the axial force and bending moment on the airframe sections. Then instrumentation, majorly what we use is K-type and R-type thermocouples, then heat flux sensor, Gordon type water cooled thin foil heat flux gauge, load cells, then deflection measurement using LVTs. Load cells are for measuring the applied concentrated loads. Then pressure transducers will be used for measuring the pressures. Now this figure shows you about what we do, how we do. So now this side we can see left side inputs, then right side outputs. In between it is the test case. Now our inputs are like time temperature profile or time heat flux profile, geometry of the article and its properties like thermophysical properties. Then based on these 3 inputs, we will calculate power requirements. Then what type of IR lamps are needed, how many lamps are needed, how much power, electric power is needed, how that setup should be made. Based on that, whether heaters are available or not, or we have to go for new heater design, then its holding, fixtures, then power distribution scheme, all the things will be worked out initially. Then after that we will see whether it can be achieved with single zone control or multi-zone control. Because it's a very large structure, then we have to go for multi-zone control. If there are different temperatures at different levels, so with respect to that we have to design a control scheme also for that. Then after that we will go for sensor bonding, where critical requirements from the design point of view, then from control point of view where sensors are needed, how they have to be bonded. There is a metallic section, of steel type, we can go for a spot welding. Directly we can bond on the hardware. If it is a composite or ceramic, we cannot weld. We have to go for a cement bonding or putty type bonding. So after that we will check the performance of the sensors, everything. Then we will go for that. And if it is a temperature control or heat flux control, that also comes into picture. If it is temperature control, we have to do in open loop or closed loop. Anyway we can do. If it is a closed loop, then we have to set gains. We have to set PID gains along with the ratings of the heater. In what region, how much heater should, maximum power that heater should be operated. Those cutoffs also we will keep. But this is based on experience only, because our complete facility, this PID is showing almost like all systems are non-linear only. Nothing is linear system here. So understanding the system is very difficult in our facility. Every system is unique. So if I work with one gain, that may not work with another system, or it may not work with another hardware. So every time I have to do a gain scheduling for everything. Then open loop heat flux control, we will do almost like we will initially, based on the heat flux profile, we will generate voltage profile. Voltage is a time profile. We will directly fed that voltage profile to heater via a thyristor. So once this is done, I will explain you in more detail about this temperature and heat flux control in the coming slides. So this figure shows one IR heater of cylindrical shape. So outputs will be again measured temperatures or measured heat fluxes and deflection based on the applied loading scheme. So this loading scheme also we have to finalize initially only after the thermal is finalized. So basic sensors are like thermocouple. So everybody knows thermocouple is mainly consists of two dissimilar metals. So if a junction is heated, then other ends we will get EMF produced. So this is works on Seebeck principle. So this EMF is measured, and based on the material data, we can convert it to corresponding temperature. Nowadays, all data key systems will directly do the calculation and give the temperature value. These are the various types of thermocouples available. Then majorly we use T-type, K-type, R-type, and B-type thermocouples, and C-type also we use. Here it is not listed. C-type C-type is mainly consists of two metals. One is rhodium, other one is tungsten material, rhodium and tungsten. So that ranges maximum up to 2300 degrees centigrade maximum temperature we can measure, but it needs inert atmosphere to go beyond 1800 degrees. Now this figure shows the two types of bonding. One is spot welding. You can see here directly bonded on the metal. So these are the two metals. This is the color code, red and yellow. So we can bond any type. We can make a junction and bond on. We can do spot welding on the metal section, or we can do individually. We can spot weld. That will make the continuity also. No, there is not much temperature difference by making the bead and bonding, or we can make like two separate welding also. This is bonded on a TPS, thermal protection system. So we cannot weld. We have to make a junction. Here we have to make junction compulsory. Here no need to make, or we can make also, because here continuity is there. Here we may not get continuity if we don't make junction. So insert junction is made, and it is bonded with a cement. Cement is mainly that ceramic based cements are having high conductivity. Now coming to heat flux. So heat flux is measured with Gordon type water cooled heat flux gauge. So its construction is very simple. So this is also some differential thermocouple principle. I can show you here. This is a one copper vessel. Like here you can see one copper vessel. Front face is completely coated with a high emissivity pane of in the order of 0.95 to 98 emissivity value. Now this side, at the center we will have a constant foil of in microns thick. So this constant foil is having welded with two copper wires. One is at the center, other one is at the edge. This edge of the constant foil is every time it is cooled with water. So you can see here, this is water inlet and outlet. So always we have to maintain the edges at room temperature. The center of the foil will experience maximum temperature. This is the temperature profile over the tungsten foil. This is a very microns of thickness. So maximum temperature we can achieve at the center will be around 170 degrees. So this is a T-type thermocouple. You can see one constant and copper is a T-type thermocouple. You can see here these are two-type thermocouple, copper constant. Now here we are measuring two temperatures. One is copper constant at the junction center, then copper constant at the edge. We have to take this difference in the temperature is directly proportional to Q. We will measure the differential EMF that is directly proportional to Q. Based on the sensitivity of the gauge, we can calculate the Q value. But this EMF will be very small, so we have to use an amplifier in between. So based on the amplifier again, we can reduce that and calculate the flux value. It is a derived quantity from the temperature difference. Now coming to temperature control. Here this figure shows the closed loop temperature control. Now I have a time temperature profile fed into the system with a dedicated software for our facility, which will communicate to every system of the facility. Now we have a PID controller. Now through PID controller it will interact to the thyristors. So from thyristors are directly connected to the heater. Now section is bonded with a thermocouple. The thermocouple feedback will be fed to the controller. So every time it will check the set point and the present instantaneous value, and based on that it will generate a command to the thyristor. That is a closed loop PID control. So here main problem is with gains. Based on the gains only it will work out. Otherwise it may overshoot or it may not control also. It may go beyond the control. That is the problem with this. So to set these gains, we should have complete knowledge about all our systems and response of the article also, how it responds to the heating, whether it is a conductive type material or it is insulated, then or what are the thermophysical properties, then what are the characteristics of the heater. So we have to consider every parameter while setting the gains. Okay. Now coming to flux control, how do we do it? Now flux control, I will generate a voltage versus time profile. Now here I will show you how I generate. Now generating voltage versus time profile for a given flux versus time profile. Now what I will do, I will have a heater. Now at what distance I want to keep my article to obtain that to simulate that given heat flux profile. So based on heat flux profile, I will select a heater and I will place my gauge at a distance from the heater. Now I will give some numerical command like I will give 10% of the rated voltage to heater and I will measure the flux. I will give 20% of the rated voltage and I will measure the flux up to its peak value. Then I will plot flux versus voltage, input voltage. So it will get a linear curve. Now we have one function Q versus voltage. Now this is the desired heat flux obtained from the designer. Designer will give flux versus time profile. Now we have to make a relation among three variables. One is flux, voltage, time. Three variables are there. Now I can do a spline interpolation among these three variables. Then I can calculate voltage versus time profile. Okay. Now this is the voltage versus time profile, which is similar to our flux profile. Only thing, this magnitudes are changed. Now you can see here at 3 volts I can achieve this almost like 14 watt per centimeter. So here you can see almost 3 volts, 14 watt per centimeter. So based on this heater characteristics, we can just roughly cross check whether this voltage profile is correct or not. Now I have to apply this voltage profile. I will apply now voltage profile to the heater. Then I will measure now again. So once I measure, now I have to compare both desired and measured value. It looks like this. Sometimes what it will do, it may not match, it may not reach the peak, it may go beyond this. So once that happens, now I have to change this part. So wherever the voltage profile, flux profile is not matching, that part of the voltage values I will change. Then I will apply that voltage to the heater and measure. So this is an iterative process till I obtain perfect matching between desired and achieved values. So these are solid one is the desired flux profile, dotted one is what we achieved. Solid one is achieved and dotted one is desired. Yeah. Now once that voltage profile is freezed, now I will remove the gauge. This time I will place the test article, and with all instrumentation. Now I directly apply the programmed command voltage. That is nothing but profile. So this time flux gauge may or may not be there. So based on the requirement, because to place the flux profile, I have to make a hole on the article to place that. So sometimes these are may allow, they may not allow also. So now with respect to that all the temperature data will be measured and compared with the prediction values. Now that is about heat flux control. Now these are the pre-test activities. Now I have already estimated power requirement based on the given time flux profile data, and I have to finalize size shape of the IR lamps. Then based on the geometry and load requirement, what test schemes should be followed, whether we have to go for a fabrication of new heater or any existing heater or modification of the existing available setups. So once everything is final, I will do a power distribution scheme, because our facility is equipped with all 36 numbers of 150 kilowatt controllers. So whether I have to accommodate everything, a complete test setup within that only. So how to distribute among these controllers? So that is planning of the distribution scheme. Once everything is planned, we'll go for bonding, calibration, checking of the health at every level, then safety at every level, because it involves electrical safety. Once everything is there, based on the control scheme, we'll go for the testing. Now, this is the general procedure followed for thermostructural testing. Once a complete test setup is ready, first we will do structural loading on the article up to design loads. Once we reach design loads, we will hold the structural loads at design load. Then we will start the heating. We won't go simultaneously for during the concentrated loads, but during pressurization we will go simultaneously. Why? Because here that application of the concentrated loads will take a lot of time, because they are sluggish systems which involves hydraulics. So that's why we will do initially, we will load up to the design load, then we will hold, then we will start heating. Once heating is over, then we will slowly reduce the structural loads. Now I will explain some 4 case studies. First case study involves multi-zone temperature control with concentrated loads on cylindrical airframe. These concentrated loads will simulate axial force and bending moment. Now in case 2, I will show how differential pressures are applied along with multi-zone temperature control on an airframe. Then case 3, I will show you multi-zone heat flux control alone, no structural loads. Now case 4, along with structural loads, multi-zone heat flux control, then actuation of the control surfaces in thermostructural testing. So now coming to this, here one cylindrical shell which is almost like 1 meter in diameter and 2.2 meters in length. So now here I have to apply a pure bending moment on this side. Then this is having 4 cutouts at every 90 degrees. Then these are divert thrusters of 3 tons each. So I have to apply 90 degrees. A critical case, 2 thrusters of 3 tons at 90 degrees I have to apply. Now this entire setup I have to close, I have to enclose with a heaters also. So how to apply this? So further what we use, we have used internal surface, internal area to apply this load. Now you can see here 3 zones of heaters are assembled. This is zone 1, zone 2 and zone 3. Then bending moment and internal 2 structural loads. Now zone 1 is having almost like 1.1 megawatt of electric power is connected. This is rated connected voltage. Test during test peak may be lesser than this. We may not go to maximum. Maximum maybe 70% of the rated power. So this is at 3 stages. Now an in situ fixture is made to apply the 2 loads at 90 degrees. Here you can see here one load is applied using 2 actuators. One other load is applied using 1 actuator. You can see arrangement. This is one in situ fixture. So I have given a hole at the center. So through this hole, I have fixed 1 actuator along this direction. Then other side, I have used 1 actuator at the top and 1 at the bottom, and I have given a linkage. Through the center of the linkage, I have connected to other side. So this way we have applied 2 90-degree loads, 3 tons of each. Then all these 3 actuators need hydraulic pumping system, which is again connected to power pack. So all these are taken out. These yellow color wires are all the thermocouple sensors. Then this also needs load cell connections, everything within that only. Now this is the complete test setup. So here you can see 3 zones of heating. Then inside it is airframe section. This is the dummy section. We cannot apply directly structural loads on the airframe section because they are designed for a factor of safety of 1.1 order. So if I apply directly structural loads on the airframe section, it may buckle locally. So to avoid that uniform distribution of stress, we have to design a sturdy structure, and we will fix to that and we will apply there. So this is a sturdy structure of almost factor of safety of 5. So here it may be higher stresses at the local zone, but as you go away from this, when I reach airframe section surface, it will be uniform. All the loads will be applied uniformly. So this is the test procedure which I explained already. I will apply up to design load, then I will hold, then I will start the temperature profile like that. So this is the 2 loads. One is compression, other one is tension. These two will create a couple. The pure bending moment is applied. So the other two are like this 90 degrees may have applied 3 tons of load. So this side it shows the 10% increase in the load, and this is during the unloading. So at this portion we have applied temperature profile. So this is the control temperature. You can see the blue line is the desired temperature. The red line traced is what I control using PID controller. This is in closed loop mode. So this graph shows measure temperature at various locations. Since duration is very high, from almost like 160 seconds, it's very fair to control the temperature. If the duration is very short, it's very difficult to follow the control the temperature profile. So in that short durations, we will go with the flux control maximum. So this figure shows the deflection data measured. So up to this 100% structural load application, this part is structured during structural load data. Then this is during thermal load applications. So this part you can see this to this almost like this is 4 mm per a D4 location. This is almost 1.5 mm. So almost 2.5 mm deflection is obtained during thermal loading. That complete detailed report will be issued. This figure shows the snapshots during the thermostructural testing. Now coming to case study 2. Here 2 airframe sections are there concentrically. Here you can see one is labeled as F1 and one is labeled as F2. Front 2 sections. So these two are concentric sections. You can see one section, then inside one more section. So this is external section, then this is internal section. Now the annular space between these 2 sections will be used for ramming the air. Between these 2, the air will be compressed and sent to the ramjet engine later. Okay, so now these sections will experience 2 types of loading. This external section will experience aerodynamic heating from externally. Then internally it will get heated up due to ramming of the air. Then internal pressurization due to this pressure, due to the speed of the air missile. Now this internal section will experience external heating. This external heating and its internal heating both are same. Then it will have external pressure and this internal pressure, both are same. Then this section will also have internal pressure, very low value, to maintain some packages. Now the challenge is to create a setup to simulate these conditions. So for that we have designed a pressure chamber and separate heating systems, everything. Now you can see this section is closed at one end and open at one end. This is easy to pressurize and test. But this one you see both sides I have to apply differential heating and internal I have to pressurize. But this is open at both ends. So closing of this end is very tricky because internal I have to assemble with heater, external I have to assemble with heaters. This section, if you see dimension wise, internal diameter is almost 500 mm, half meter. Then length is 2.8 meters in length. So these are the controlled temperatures. Then this is the controlled pressure, simultaneous controlled pressure over the trajectory time, almost like 0 to 470 seconds duration. This is the one external F1 section before and after the test. Then this is F2 before after the test. Here I will show you the setup. So this is the heaters design. Here this is the F1 section. The internal it is assembled with 4 zones of heater. Externally also assembled with 4 zones of heater. So these are the realized heaters. Once heaters are assembled, it will all the heater connections will be taken from inside the frame. Then top side I have to close this frame only I have to use to close the heater airframe F1 section. Then external heating. Then I have to place F1 section over this. Then over that again I have to place heaters. Then this entire thing should be closed in a chamber. This is the complete test chamber. So now I have to take everything inside, like all the power connections. For that we have designed separate cable penetration system based on IEEE 377 standard. Then here we have to take all water connections inside. This complete thing should be hermetically sealed because operating pressure is pneumatic pressure at 10 bar pressure. So this is you can see here top side of the F1 section is closed. So the internal arrangement is like this is the F1 section. This is the lid what you can see in the top figure. So this is a rubber seal. So that is this is the seal. It's called actuator seal. Then there is a retainer ring. Whenever this is pressurized, this rubber seal will get intact with the F1 section. It will hold the pressure there. Here one more constraint is the axial force coming onto the lid should not be transferred to the airframe section. That is the main constraint. That's why we have to make a rubber contact between this metal and metal section. Now this is the result. You can see this is the actual T0 is 300 seconds is the T0. To get initial 10 bar pressure, initially we are doing a slow increase in the pressure, later we are doing. So this is the controlled closed loop temperature control, and this is the controlled pressure over the complete range. This is almost fast forward simulation animation made in MATLAB, but actual time it is almost 777 seconds. So this portion is mainly due to the natural cooling of the section. We cannot maintain this. This can be achieved in the flight due to the movement of the missile. But here it is in static condition. I cannot achieve the perfect matching of the problem. Heating are perfectly maintained. Now coming to a case study 3. Here I will explain you 2 zones of heat flux control. So this is one airframe section which is having a connector here. You can see here this is a connector. Okay, inside 2 connectors are there, cable connectors. Then from outside it is having a metal casing. Inside metal casing. Now whenever this get aerodynamic heating, then these cable connectors should not melt and short the cables. So for that I have to do a instrumentation on connector, cable level and panel level, inside the panel, external to the panel. Then we have made a setup and did differential control, because this section will undergo rolling. Due to rolling, it will have different heatings at different times. So due to that also we have created a setup. So now this is the panel cup after the thermal testing. So for this we have developed a separate simulating code to apply 2 differential heat flux profiles on the airframe section at different levels, different sides. So these are the 2 heat fluxes which are applied on the section and qualified the connectors. Then next one is this one composite fin. Here you can see a composite fin. Okay, actually this construction of the fin is with aluminum structure inside. Externally it is having all the carbon phenolic plates. Okay, now this leading edge is made up of carbon and fin tip also carbon. Here during thermostructural testing, the fin also should actuate because it is directly connected through a shaft to actuator. Actuator is placed inside the fin. So in this fin is almost like very big. You can see here 755 mm in length, height, and 920 mm in width, and total thickness of the fin is 125 mm. The exhaustive instrumentation is used. 55 thermocouples of K and R type. 2 heatless gauges are mounted and 6 LVDTs, 5 loads. Here 1 load on the tip, 4 loads on the panel, inboard panel. So during the setup, this is loaded. At one point of time, the load should be removed, and this we have to do an actuation of this also. So how to remove that load? For that also we have worked out a scheme. Then 33 strain gauges are also bonded. So this is the complete test setup of solid module. This is one of the flux profile. This is a multi-zone. 5 different heat flux profiles are applied in this test setup. That's why different segments are used, different power schemes are worked out for this. This is one of the heat flux control on the inboard panels. You can see here during video. So this is during the testing. So at the end of this test, you can see an actuation. Here, this is the load onto the fin. Directly fin tip is connected to this load. This vertically I have placed one more actuator to delink the load during actuation. Whenever I delink, yeah, here it is delinked. Now it will start actuating. Now that you cannot see here. Now you will see once this comes to the end. Actually, this test duration is 1 minute. So here I have made a cut also. So this is a complete carbon phenolic airframe section. That's why it will give lot of smoke due to the burning of the phenolic. Here you can see actuation of the fin in red hot condition due to Thermo-Structural testing. Okay. So this is all instrumentation is there in this. Now another thing what we have developed very recently is, see, whenever I assemble one over the other heaters with C-band clamps, here you can see from here to this end almost I am getting uniform heat flux distribution, but from one end to other end there may be dip in the heat flux. This we call it as dark zone. This dark zone for C-band lamps is almost like 50 to 60 mm. If I place very far away from the section, it doesn't matter. But if I place very close to the airframe section, in that case, this matters. This zone may not get heated up. Okay, airframe section may not get heated up in this region. So for that, we have designed separate straight lamps and arranged in this fashion. One slot in the one heater, other slot in the other heater, like that. So we have maintained very close distance of 30 mm. This 30 mm between these two lamps also maintained. In this way, we have reduced a dark zone to 20 mm from 50 to 60 mm to 20 mm. So for this here, one major challenge is bringing this ceramic cap into the IR region. Now you can see here ceramic cap is at the back side of the IR, so it may not face that much heating also. Here this complete thing will get heated up. So what is happening? Initially when we brought this ceramic cap into the IR region, every time this there will be a joint here actually. Now if you see lamp inside of the ceramic pen, that quasi tube is fixed there, then from that, so that it is leak proof from there. So whenever it is bonded to this, then that gases are leaking, that joint is cracking and this lamp also getting leaked, so inside gases are leaking. So what we made a special simple link. So here you can see through this hole, one side we made a hole, other side we have taken a wire. This wire is directly welded through this hole to the filament using molybdenum foil from the bottom. So this is simple link. So now there is no bond between ceramic, this quasi tube and the ceramic cap. So this is a simple joint. So due to this, that bonded cap is temperature is not at all increasing beyond 150. If it reaches beyond 250, it will get the joint, inside joint will break. So now we have done for very long duration, almost 100 seconds we switched it on. So it's nothing happened in open rack condition, not in assembled condition. So no, in this way we qualified that lamps. Then power ratings also it is matching. Due to this, we have reduced almost 75% cost compared to this C-band lamps. Then dark zone also 40% reduced. So at final, I want to tell, I will give you just brief about our facility. Our facility has a maximum power of 755 megawatt electric power connection. Electric substation is dedicated for our facility. We have 36 channels of 150 kilowatt controllers and 64 isolated DAC channels for temperature and 256 non-isolated channels. Then 32 zones of closed loop and 16 zones of pressure, and maximum heat loss we can simulate with IR is 2.1 megawatt per meter square. Then maximum pressure in the one of the case of the chamber, it is designed for 50 bar, but maximum we have tested up to 20 bar. So these are the various types of instrumentation we use. So finally, I want to thank Professor Gopalakrishnan and Nilesh Mehta for inviting me to give this webinar in INAE Bangalore chapter. I thank INAE also. Then I thank our DRDL team also. So thank you all the participants for your patient listening. Thank you, sir.
Thank you. Can you hear me, Narender?
Yeah, yes, sir. Yes, sir.
Thank you very much for the talk. There are several questions now.
Yes,
so what I will do now is read out the question and you kindly answer it.
Yeah.
So the first question is by Dr. Atre. The question is, how did the lab test compare with the actual flight data?
Okay, sir. Actually, flight data, after the flight, they measure at various locations. Actually, flight test it is due to convection, sir. Okay. The flight environment is convection. So whatever our lab environment is radiation. So due to this different heating mode, there may be slight variation in the measurements. So apart from that, not much abnormal changes are measured, because in one Astra flight we have compared with the ground test data with the flight data on one of the electronic package. So that is very well it is matching, because package is directly mounted inside the airframe section. So in whatever the way the airframe section is get heated up, inside the phenomena inside the airframe section is inside the heating phenomena is similar. It is like through conduction and internal air convection. Through that only that package will get heated up. So that data we have compared with our ground test data is perfectly matching, sir.
Thanks. I'll ask one more question, and before that, a request to the audience: if you have any questions, please type your questions in the Q&A, and we'll take them up one by one. Okay, next question is by Professor Padhi, yes. And the question is as follows: if complete knowledge about the system is needed to tune the controller, why not use a non-linear PID controller? It may avoid the difficulty of gain scheduling.
Yeah, yes, sir, correct only. But actually, our systems are like. One is there is a delay in our DAC system, starting with the DAC, then from the DAC to the thyristor, there are two more linkages are there, like primary MCCBs, then secondary MCCBs, then contactor, then thyristor output to the isolator to the heater. So all these systems behavior, we don't know, sir. Actually, these are all bought out systems. So how they behave, that complete mathematical model also we don't have. So what we are doing every time, by giving an input, by measuring the output, how it behaves. So that based on that data, we made a data sheets. So through that we are finalize some gains. For this particular gain, for this particular rate of heating on this particular material with this thickness, we can achieve fairly. Like that we made one tables after doing rigorous testing only, sir. That's why we are doing, but we don't have complete mathematical model also to develop a nonlinear PID control, sir.
Thanks. Next question is just one second. Yeah, it's by Professor Jagdish. So I'll read it out. The question is, do you have any in situ measurements or diagnostics to understand how the structure reacts to both thermal and structural loads? And there's a clarification to the question. What I meant is any time-dependent visualization methodology that gives quantitative or qualitative information on the behavior of the structure, not just point measurements.
Okay. So that we don't have, sir, now. We are qualifying this section from thermostructural loads only after the test by doing a visual inspection and doing radiography. Then even in this test, one more thing, we are qualifying with respect to deflection measurement only. We don't have strain measurement also at high temperatures. So only through visual inspection and deflection data, and from the NDT test only we are qualifying it, sir. But no online and in situ measurements are not there with us, sir.
Thanks. One more question. This is from Dipankar Banerjee. The question is, what kind of load and displacement sensors are used when temperatures are very high, say 2000 degrees centigrade?
Yes, sir. Actually, what we are doing is that LVDTs. What LVDTs are used, sir? Linear variable differential transformers are used for load deflection measurement. During that LVDT is connected with a rod. That rod is having insulation. We do a wrapping on the rod. So that is with one silica foam. Then after that we do a high temperature tape on that. So that can withstand almost like 2000 degrees, sir. So that way we protect that metallic rod. So that heat should not go into the sensor. On the sensor shell, we will assume that it is a room temperature. So that's why we are protecting the sensor. Then one more thing, in some cases we are using extensions because some places maybe we don't have access to place the sensor inside the setup. So that's in that cases we place the sensor outside the setup and we do a extension rod with complete thermal protection. That's why we do, sir. Then all load cells are directly connected to the our hydraulic actuators. Then through connecting rods. So we may not directly heat up. That load cell may not see direct heating. So that is also wrapped with silica cloth, annual silica cloths. That's it. Because that sensors also has temperature limitations. Otherwise, it may not work. All the electronic circuits inside this.
Thanks. There's one question from Mr. Gopinath from Aerospace Department.
Yes.
He has two questions. I'll ask them one by one. The first question is, does dynamic pressure play a role in IR-based thermostructural testing?
Sir, can you repeat, sir, please?
Yeah. Does dynamic pressure play a role in IR-based thermostructural testing?
Actually, what it will do is, this is actually whatever I have shown in the slides. That is requirement from the Russians. That is given by Russian designer, so that we have to simulate exact pressures seen by the missile. So in many cases it is not possible to simulate the pressures, but in this case we have attempted to simulate that pressures. Otherwise we can do a equivalent structural load and apply also. Both way it is possible, but here it is possible to simulate the dynamic pressure. That's why we have simulated in that particular case only. Otherwise, in other all sections it is not possible also, sir. So that's why we go with the concentrated loads with hydraulic actuators.
Okay, and the second question is, for hypersonic vehicle frame, can IR-based thermostructural testing, is IR-based thermostructural testing sufficient, or does it need other testing like arc jet and oxyacetylene tests, etc.?
Yes, sir. Sir, actually, thermal test point of view, flux simulation limited, sir. So as I said, this is maximum we can simulate 2.2 to 2.1 megawatt per meter square flux only. But in hypersonic vehicles, we see in the order of 8 megawatt per meter square. Then during re-entry, sometimes it may go beyond 10 megawatt per meter square also. That is not possible with IR, sir. So in that cases, maximum what we have simulated is 3.4 megawatt per meter square flux for re-entry vehicles using graphite heaters. So in an atmosphere, maximum is 3 only, sir. Beyond that we cannot test in ground. But arc jet and all, that it may be limited for a smaller area, not in like 1-to-1 scale. Maybe we cannot simulate that heating, sir. But sample level we are doing with that.
Thanks. One more question from Dipankar Banerjee. And the question is, what are the maximum temperatures you can get, and what are the time periods taken to achieve those temperatures?
So actually, maximum temperature till now we measured is 2300 degrees centigrade on silicon carbide samples only, sample level testing में CSIC samples with C-type thermocouple in inert atmosphere. So in that case, maximum rate of heating we can achieve is almost 100 degrees centigrade per second we have achieved, sir, in with this IR, but for very short duration. It is almost like the complete heater, what I have shown, planar heater, it is sustained for maximum 30 seconds only. So beyond that, all the lamps were broken. So that one of the maximum that only we have till now tested on sample level.
Okay. Just 1 second. I think I have checked all the questions. If there are any questions, kindly do type them. Otherwise, I'll just make a quick announcement. Okay, no more questions. So in case there are questions, please type them. So thank you, Narender. Thank you very much for your time and for helping us launch this webinar.
Yes.
Also, thanks to all the attendees for attending this webinar. My apologies for the initial pause. I really didn't know if you guys were able to see it or not. So I think I'll get more experienced at this. So a request to all of you, please do join the webinar next month also. We are planning to have this once a month on different topics. This time it was aerospace, next time it'll be civil, it'll be computer science, it'll be all over the place. INAE has pretty much everything under engineering under it. So please do join. The time will be always the same, 6 p.m. to 7 p.m. I think we'll go with the 4th Thursday of every month or the 3rd Thursday, depending on availability. And if there's any feedback, please do write it. Please do email me. You can Google me. Nilesh B. Mehta is my name. You will find my email ID. Instead of typing the email, you can just Google me and send me an email ID. Any feedback would be very helpful so that we can make this a very productive and very interactive webinar. It was very nice to see so many questions today. Thank you all. And goodbye and good night.
Thank you.
Thank you very much.
Thank you.